So 1.6, which feels like it's been forever since we actually did a lesson, is all about complex numbers. Bless you. So complex numbers are sort of a topic in math that sort of got the short end of the stick when it came to naming. Complex numbers, imaginary numbers, it makes it sound like it's something really hard or something completely fake. But it's the exact opposite. It's actually pretty straightforward, and it's as real as, say, the number 2 or 5. So let's start with the definition here. If we're going to talk about complex numbers, we have to know what the heck they are. So, a complex number, so that's the vocab word there, a complex number is an expression of the form a plus bi. That's it. It's simply a number that's made up of two pieces instead of the traditional one piece that we're familiar with. Now, there are some restraints, or there are some descriptions of all these pieces here, the A, the B, and the I, where A and B are real numbers. So this symbol here, A comma B, this weird funky E, and the double stroke R, simply means A and B are just any ordinary real number that you can think of. Bless you. And this is the thing that makes imaginary numbers imaginary. This I here is by definition the square root of -1. And if you're interested, it's called the imaginary unit. Yeah. Again, like I said, it's sort of unfortunate that it was called imaginary numbers, but they're as tangible as, say, the number 2 or number 5. A and B themselves do have special names. A is the real component. And B is the imaginary component. So there are some important definitions we should know. This I here, we call it the imaginary unit. And in this definition of a complex number, the A is the real part, and the B is the imaginary part. Right. So those are the linkage. Those are the important vocab words. Just to make sure that we understand the vocabulary, I'm just going to write down a handful of just random, not so special complex numbers. Say, 3 plus 4i. Say 1/2 minus 3/2 i's. Let's do just a random imaginary number, 6i, or a random real number, -7. In the first example, I would say 3 is the real component, and 4, just the 4, not the 4i, just the 4, is the imaginary component. Right. So following the trend, in the second example, I would say that 1/2 is the real component, and therefore -3/2 is the imaginary component. Technically, by definition, a complex number has those two pieces, always, A plus BI. So if you had a singular piece, say 6i here, technically it still has both parts. So what would the real component of the third example be? 0, right? It's the number that doesn't have an I attached, so it's 0. So in this case, 0 is the real component. 6 is the imaginary. And for the last example, it's just the same but flip-flopped. -7 is the real component. And 0 is the imaginary. Right. So that's what makes that's the complex in complex numbers. The word complex in this context simply means more than one, right? So it doesn't mean difficult, it just means more than one piece. Well, if you can visualize complex numbers as these two pieces, then you should know how to plot them or visualize them. Because these numbers are two-dimensional rather than one-dimensional, we cannot plot complex numbers on a normal number line. Normal number line is only one dimension. We need a two-dimensional field to plot complex numbers. That field is what we call the complex plane. Or if you want to impress your future professors or friends at parties, you can call it the Argand plane. Yeah, you guys don't talk about complex numbers at parties? You guys are going to the wrong parties then. Argand. Argand. I think it's some guy's name. Yeah. So the way you plot complex numbers is nearly identical to the way you plot regular Cartesian planes. So instead of a normal XY graph, instead of XY, we instead have a real and imaginary graph, right? So that's the only difference. Instead of XY, you have real and imaginary. So let's make up a random complex number, and the letter we typically use for complex numbers is Z. Say we had 2 minus 3i. I hope everyone can see that it's the real part is 2, and the imaginary part is -3. So that's what you literally graph. On the real number line, you go to 2 tick marks. On the imaginary number line, you go to -3 tick marks. Boom. There is Z equals 2 minus 3i. So although it is technically one number, because it's made up of two pieces, we sort of plot them like regular coordinates. Easy peasy? Yep. So to plot complex numbers, you use graphing coordinate skills. What other things can we do with complex numbers? Well, anything regular numbers can do, complex numbers can do as well. We can add numbers. 2 plus 5 is 7. We can subtract numbers. 10 minus 3 is 7. I guess I like number 7. We can multiply numbers. We can divide numbers. All of those we can do with complex numbers. It does require a little bit of different skill sets, but skill sets you already have. So the idea is adding, subtracting, and multiplying requires polynomial skills. In other words, how you add, subtract, and multiply polynomials is precisely how you add and subtract complex numbers. Let's review. What is the technique when you add and subtract polynomials? What do you do if I put a polynomial plus another polynomial? Not conjugates.
Add them.
You add them, so how do we add polynomials? What's the technique? Maybe you guys need to see an example. Say, yeah, what do we call it when you put the same variables together? It's combine like terms. That's it. That's all adding. Yeah, that's all adding, subtracting really is. To add and subtract polynomials, it's just combining like terms. Guess how we add and subtract complex numbers? It's combining like terms. When it comes to multiplying polynomials, what's the technique or the strategy or the method we use? Just distribution. It's all it is repeated distribution. Some of you guys like FOIL, call it that. Guess how we're going to multiply a complex number? Distribution, FOIL, whatever you want to call that. Right. So to add and subtract and multiply complex numbers, we don't have to learn new things. You guys already have the skill sets to do it because it's just doing the same thing with polynomials. So let's just do quick examples here. Say I have the number 5 minus 3i, and I want to subtract 2 plus 8i. Right. You could easily change those i's into x's, and the skills will be 100% the same. Just combine like terms. But for subtraction, I like to distribute the negative because that sort of trips up some students. And then once you distribute the negative, just combine like terms. Here are my regular numbers. Here are my I numbers. The only thing that's different between polynomials and complex numbers is in polynomials, I always tell you to write the variable first. It's sort of backwards for complex. We always write the i's second. So I'm going to write the regular number 3 first, and then the minus 11i second. Easy peasy. Can I assume that we all know how to FOIL? We all know how to distribute? Yeah. Anyone need to see an example of multiplying? No. All right. But there is one thing I do want to touch base that is related to multiplication. And those are the powers, or the exponents of I. So recall that I, by definition, is the square root of negative 1. So if I were to put an exponent on this I, say a square, all I'm going to do is wherever I see an I, I'm going to substitute a square root of negative 1. So in this instance here, it'd be the square root of negative 1 squared. And I hope we all know that a square root and a square, they cancel each other out, gives you negative 1. You guys get the idea? Yeah. So I'm going to do the same thing for a cube. I'm going to do the same thing for the 4th power. I'm going to do the same thing for the 5th power. First and third hour really didn't care for it. So I'm going to skip the work, and I'll just write down the result. But just know that's exactly what I'm doing. So let's start off with I to the 0 power. Properties of exponents, anything to the 0 power is 1. I to the 1st power, anything to the 1st power is itself. I squared, we just did, was negative 1. And I cubed, if you went ahead and did I cubed, square root of negative 1 times the square root of negative 1 times the square root of negative 1, did the math, you can get negative I. I to the 4th power, if you did the math, you're going to get a 1. I to the 5th power, if you did the math, you're going to get an I. I to the 6th power, if you did the math, is negative 1. I to the 7th power, if you did the math, is negative I. I to the 8th is 1. I to the 9th is I, so on and so forth. The reason why I'm writing out this list is that I, the imaginary units, off the top of my head, now I don't know all of math, so I could be telling you a lie here, but as far as I know, off the top of my head, I is the only number that does this. Typically, when we use bigger exponents, the numbers change. Any number you can think of, with the exception of 0 and 1, will change as you use an exponent. 2 to the 1st is 2, 2 to the squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. It's constantly changing. But if you take a look at the exponents of i's, notice the answers, the powers. 1, I, negative 1, negative I. 1, I, negative 1, negative I. And if I continued it, 1, I, negative 1, negative I, if we continued it. So the powers of I are unique in that they repeat. I cannot think of any other number that does that as you use an exponent, they repeat over and over and over again. So when it comes to powers, I usually expect you to memorize it. I expect you guys to know what 2 to the 1st power is. I expect you to know what 2 squared is, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. I expect you guys to memorize all of those. But because the powers of I repeat every 4, you really only need to memorize the first 4. And then everything else after that is just a repeated pattern. So that's one cool thing with i's. So when you're multiplying complex numbers, you may get I squares, you may get I cubes. I expect you guys to simplify it. So the moral of the story is, you can always simplify i's if it has an exponent. If this was a quiz or a test and I said simplify and you had an I that has an exponent on it, there's always more you can do. Okie dokie? Yeah. Now for smaller powers, that's easy. What's I to the 6th? Okay, I can run through the pattern. What's I to the 10th? Oh, I can run through the pattern. But if I gave you something like, what's I to the 839th power? I don't want to run through the pattern over and over and over again 8,319 times. So here's the idea. The powers of I repeat every 4. That's what we saw in the pattern, yes? So in all of those exponents, the 8,319 exponents, I know every 4 groups of exponents is a duplicate. So I want to strip off. I want to take away all of those duplicate exponents. So I'm thinking, okay, how many duplicates of 4 are there in 8,319? That is a division question. So what we're going to do is we're going to take the exponent and divide it by 4. Now this is the one time I would not use a calculator. I'm going to go old school. Yes. Long division. So you divide. 4 goes into the 8 2 times with no remainders. Bring down the 3. 4 does not go into 3, 0, with a remainder of 3. Bring down the 1. 4 goes into 31 7 times with a remainder of 3. Bring down the 9. 4 goes into 39 9 times with a remainder of 3. Right. So all of this work tells us in the exponent of 8,319, we have 2,079 groups of duplicates. Those are the ones we can throw away because they're duplicates. I am interested in the remainder. So all of this work says I to the 8,319 is the same as I cubed, which I hope we can then go through the pattern and just know off the top of our heads that that's negative I. Right. So that's the idea. If you ever have to do an exponent of I and it's wickedly crazy, don't spend 5 minutes going through the pattern. Divide the exponent by 4, you keep the remainder. Question?
I don't know if it just works for this one,
Uh-huh.
but for every multiple of 4, I know that I don't think we'd have to pay attention to the 8 and the 3.
Okay.
Just the 1 and the 9. At 16, that's the 4, the first 4, and then 17, 18, 19, 20, that's the next 4.
I think that would work. However, 83 is not a multiple of 4, though.
But that shouldn't matter because you know 100 is bound to be a multiple of 4, so you just need to pay attention to the last 2. Or even the last.
Oh, I see what you're saying. If you strip off 8,300, you only look at the 19.
Yes.
Yeah, that would work, always.
Okay.
Good observation. Yeah.
Every single number?
Say again?
For every single number, just this one?
When you're divided by 4.
Oh, okay.
Neat.
That class will teach you something.
So, we know how to add, we know how to subtract, we know how to multiply complex numbers. That's just adding, subtracting, multiplying polynomials. Dividing is its own separate beast. Because, and I hope you guys know 3 dots, upside down triangles, because I equals the square root of negative 1, I is actually a radical. Dividing by a complex number puts a square root in the denominator. G Have we done something recently on, I don't know, a quiz where we had to fix a square root in the denominator? What do we call it when we get rid of a square root from the denominator?
So I got all those.
It's called rationalizing, yes. So that's the technique when you want to divide complex numbers. Now, yes, someone mentioned, I didn't do so hot on that section in the quiz, so this might be a good time to pay attention. Let's kill two birds with one stone. Let's divide complex numbers, and let's refresh our memories on rationalization. Therefore, the technique is to rationalize. So that's the idea. Dividing by a complex number, rationalize. You should link those two ideas together. Dividing by a complex number, rationalize. We did two types of rationalization examples in 1.5, I believe. It was when you have a monomial in the denominator and when you have a binomial in the denominator. And there's different techniques for both of them. So let's take a look at two examples here. Let's suppose I wanted to divide by 7 plus 3i over 4i. Hopefully everyone can agree that this is a monomial in the denominator. There's only one piece. So if there's only a single square root in the denominator, the technique is to multiply by itself. Now, since the only thing I want to rationalize is the I, I'm going to multiply by just the I. A lot of people on the quiz, they multiply by the coefficient as well, which is not wrong. It just makes your problem a little bit bigger and you have more simplification. I just go ahead and multiply by the thing I want to get rid of. And then you just do math. Distribute. That's 7i plus 3i squared over 4i squared. And we just have to remember, I suck at drawing thought bubbles. We have to remember that I squared is negative 1. So wherever I see an I squared, that becomes a negative 1. So when I squared is negative 1, everyone agree that this becomes a minus 3? I squared becomes a negative 1, that becomes a minus 4. So we get 7i. We get 7i minus 3 over negative 4. Okay. So far, so good?
Yeah.
Okay. Technically, however, more thought bubbles. Or thought clouds, rather. Complex numbers in standard form are always two separate pieces. The real first and the imaginary second. What we have here is it's backwards. The i's are first and the real part is second. And also we have one giant fraction. So we need to do two things here. We need to split apart the fraction. Each piece will get its own denominator of negative 4, and then I need to swap them. So this will give us positive 3/4, negative 7/4 I. I did two steps at once there. Please let me know if you're confused, and I'll show the middle step. We okay with what I did there?
Yeah.
Okay. So that would be technically the perfect looking answer in standard form. So dividing by a monomial is just rationalizing a monomial, which is just multiplying the numerator and denominator by the thing you want to rationalize. In this case, it's an I. The real work, which is not a lot of work to begin with, is when you have a binomial in the denominator. Let's say I wanted to divide 3 plus 5i by 1 minus 2i. The idea when you want to rationalize a binomial, now this is the time to say it, Patrick, is to multiply by the conjugate. 1 plus 2i, 1 plus 2i. And then you just go ahead and repeat, distribute, or FOIL if you call it, and then you're done. So that's going to be a 3. 6i plus 5i is an 11i plus 10i squared over, and now in the denominator, you shouldn't have to FOIL. You should know that the difference the product of two conjugates is the difference of the perfect squares. Right. So in the denominator, I don't need to FOIL. I know it's going to be the first guy squared. 1 squared is 1, minus the second guy squared. 2i squared is 4i squared. We all know that I squared is negative 1. So everyone knows that 10i squared is a negative 10. And then a minus 4i squared is going to be a plus 4. Everyone okay with that? Go ahead and combine like terms. So in the numerator, we have a 3 with the negative 10 is a negative 7. And then in the denominator, we have a 1 plus 4, which is a 5. I want it in standard form, so just split apart the fraction. Negative 7 fifths plus 11 fifths I. Right. Easy peasy. Looking at this example, you probably wonder, man, why was it so hard in the quiz? Alex, you said you got this part wrong. Is it understandable now?
Yes.
Okay. So the moral of the story is, eyes are not, well, they are new. They are new when it was invented, but to handle them, to manipulate them, to do math, these eye stuff, it does not take new skill sets. Thank you.
Yeah, take home.
Yeah. Okay. Just remember, at any time in your mathematical career, if you have to take the square root of a negative number, say the square root of negative 50, don't freak out. Don't say I can't do this. Don't write no solution. All that negative does is you just pull it out with an I and make the radical positive. That's all you have to do if you're solving an equation, if you're simplifying, whatever you're doing. If you have to take a square root negative, just pull that negative out with an I, and then you go ahead and simplify as normal. That's 25 times 2, which is 5i radical 2, right? So that's it. I's imaginary units. It's a simple definition that allows us to do so much more math than real numbers could ever do for us. That's 1.6. That's it.